I would like to finish now the topic of isomorphism theorems. We have already seen the first isomorphism theorem that said that if R is some commutative ring, and if we take a homomorphism of modules over this ring, then we prove that co-image is isomorphic to image. So co-image is m factor by the kernel of phi is isomorphic to the image of phi. And this is basically one isomorphism theorem to rule them all. The second and the third isomorphism theorems are analogous to the ring case, and they are also proved by applying the first isomorphism theorem. So the second isomorphism theorem says that if we have K and L, two submodules, then considering the submodule K plus L, the submodule generated by K and L inside M, and quotienting it out by L, will give us a result isomorphic to the quotient of K by the intersection of K and L. Just as we showed for rings and ideals, we prove it by first considering a homomorphism from K to K plus L mod L, where we send an element K of K to its representative, K modulo L. First, we want to describe the kernel of phi. So we say that K belongs to the kernel of phi if and only if its image is equal to 0, which is the equivalence class of K. And this happens by the definition, by the construction of the quotient module. It happens exactly when K lies in the submodule L. So we started from K in K, so we conclude that the kernel of phi is exactly those elements of L which lie in K. And now we can see that phi is surjective because any element of K plus L mod L is written as the equivalence class of K plus L for some representative K plus L with K in K and L small and L capital. But this is equal to the equivalence class represented by just K because L is in this submodule. And this is the image of K. And so by the first isomorphism theorem, K plus L mod L we show that this is equal to the image of phi. This is isomorphic to K mod the kernel of phi. So this is what we wanted to show. And the third isomorphism theorem says that if we have k inside L inside M, so for both k and L are submodules, then M mod k further modded out by L mod k is isomorphic to M mod L. Just as in the ring case, the third isomorphism theorem is about cancelling denominators. The proof of the third isomorphism theorem follows the same logic. So first, observe that L mod k is indeed a submodule of M mod k, because any element that is 0 in L mod k can be represented by an element from k, and so it is also 0 in M mod k. And thus we can write this quotient. So this quotient is well defined. And now I want to define the map phi from M mod k to M mod L. By the universal property of quotient, giving the map phi is the same as giving a map from M to M mod L that vanishes on k. And this map is given by sending M to the class represented by M. And since k is inside L, the submodule k is sent to 0 in M mod L. So this map factors through the quotient, and phi is well defined, and it sends an equivalence class represented by M to an equivalence class represented by M, but now in this M quotient by L. It is evident that it is that the homomorphism phi is surjective, because we take some representative M of an equivalence class here, and its preimage here would be a class represented by the same element. And now we want to describe kernel, so an element, an equivalence class is in the kernel of phi if and only if it is 0 in M mod L, which happens if and only if M belongs to L. And this happens if and only if the equivalence class in this module lies in the quotient L mod k. And so again, by the first isomorphism theorem, we have that M mod L, which is the image of phi, is isomorphic to M mod k, further mod out by the kernel of phi, which is L mod k. And this is what we wanted to conclude. Just as in the case of rings, we have the following proposition. So let's say that K is a submodule of M. Then we have a natural bijection between submodules of M that contain K. And submodules of the quotient module. Let me remind you how the bijection is constructed. If I denote by Q the quotient homomorphism, where Q of M goes to the equivalent class containing M, then if I have a submodule of M such that K is contained in L, then I define the map from the left to the right by taking L to its image in the quotient module, which is L mod K. And this is a submodule of the quotient module. And conversely, if we have a submodule M inside M mod K, then I associate a submodule of M, which is the pre-image under this surjection. And this submodule of M contains K, because in particular it contains the preimage of 0, which is the kernel, and K is exactly the kernel of Q. I omit the checks that these two squiggly arrows define mutually inverse bijections. I will now start discussing free modules. I said that modules are like vector spaces over rings, but that modules have many weird properties that distinguish them from vector spaces. So free modules would be as good as they can be to mimic vector spaces. So what do we know and like about vector spaces is that they have well-defined notions, well-defined notion of dimension, and we have basis for them. So a basis is a subset of a vector space that generates the vector space and is linearly independent. And so let us now start with defining what does it mean that a subset generates the module. Let's fix some commutative ring R and an R module M. And for some subset of M, not a submodule, but subset, probably infinite, we say that RA will be the set of all finite linear combinations R1 A1 plus Rn An, where n is a non-negative integer, and for every I from 1 to n, Ri is a coefficient in the ring, and Ai is an element of the set. So this will be called the submodule generated by A. Note that this is a submodule indeed, so Ra, this set forms a submodule. Because, so it is a subset of M. Because if we take a sum of these two finite combinations, it will still be a finite linear combination of elements of A. And if we multiply it by some scalar s, then by replacing Ri's with SRI's, we again get an element of this form. And compare this to the definition of generators of an ideal. So an ideal is a submodule of R, and we say that a subset of this ideal generates the ideal if it generates it under finite linear combinations and multiplication by elements of R. So let's see what examples we can come up with. If R is equal to Z, then Z mod 2Z is a Z module. And it is generated by 0 and 1, or by just 1. Okay, so generated by 0 and 1 trivially, because this is just a whole module, and by 1 because we can get 0 by multiplying by the 0 element of the ring. And in particular, any finite C module has a finite set of generators. And in this case, when we have a finite set of generators, we say that M is finitely generated. If M is equal to Ra for a finite subset A inside M. So, okay, all finite modules trivially have a finite set of generators, but so do some infinite modules. For example, we can consider z to the power n, and it is generated by the finite set of vectors, standard basis vectors, 1, 0, 0, 0, 0, 1, 0, etc. till the end. So by n vectors generated by by n elements. And if R is any ring, then in the same fashion, R to the n is finitely generated. And if f is a monic polynomial, then we proved that R adjoint x mod f is isomorphic to R to the n as abelian groups. But in fact, this isomorphism holds as modules. And so for a monic polynomial f, R adjoint x mod the ideal generated by f is finitely generated, and the set A, we can pick it to be elements 1, x, x squared, etc., all the way to x to the power degree of f minus 1. We can consider certain examples which are of modules which are not finitely generated. Again, starting with the case of the base ring Z, Q is not a finitely generated module. Z module. So how do I show this? Arguing by contradiction, take any finite subset A of Q, where A is, if I denote its elements by A1 through AN, and we can pick a common denominator for all AIs. Denominator, so that AI is equal to some BI over D, where BI is an integer and D is a positive integer. But then the submodule, the Z submodule generated by A, will only consist of these rational numbers whose denominator divides D. We'll have denominators that divide D. So for example, element 1 over 2D, it is a rational number, but it will not lie in the submodule generated by A. And so any finite set does not generate the whole Q. And so Q is not finitely generated. However, we can pick A to be the set of all 1 over D for all possible denominators. So D is a positive integer. And then A will generate the whole cube. But this A is infinite. So also R is not finitely generated over Z, and S1 viewed as complex numbers of length 1. They are all not finitely generated over Z. So here S1 is defined as the set of complex numbers whose length is equal to 1. So these are all the complex numbers on the unit circle. And the operation that we take for addition is multiplying these numbers. So it is an additive operation, so we can view S1 as an additive group, and therefore it is a Z module. So if I multiply this element of S1 by this element of S1, I need to add argument of 1 to the argument of another, and so we get something here. Another non-example. Let's take any non-zero commutative ring, and then the set of all polynomials viewed as an R module is not finitely generated. So we argue the same way as for Q. So take any finite A inside R adjoint X. But then we can, because we only have a finite number of polynomials, we can bound their degrees. So there exists n, such that for every A in A, the degree of A viewed as a polynomial is at most n. And we are only allowed to multiply polynomials by scalars, which does not change the degree, or even worse, it can decrease the degree. So the submodule generated by A has polynomials of degrees at most m2, but R of X contains polynomials of arbitrarily large degree. Recall that for vector spaces, if F is a vector space, then any vector subspace of a finite dimensional space is finite dimensional itself. But it is not true that a submodular finitely generated module is finitely generated. So, warning. a submodule of a finitely generated module need not be finitely generated itself. And although it is not Halloween, here is a spooky example of how this may happen. Let's take for the ring R the ring of polynomials in an infinite number of variables, x1, x2, x3, etc. Ring of polynomials in an infinite number of variables. Then R is generated by the set consisting of 1. So it is finitely generated. But let us consider the ideal of R generated by all the variables. So x1, x2, x3, etc. It is an ideal in R. So this ideal is not finitely generated. And this is because, again, start with any finite A in I, finite subset. So this subset does not contain, there exists none such that xn doesn't appear as a summand in any element of A, because we have only a finite number of polynomials in A, and these polynomials have a finite number of summands. So xn cannot lie in the submodule generated by A. I guess I will leave it at that. Now we are arriving to the notion of linear independence. So when our subset, which possibly generates the whole R module M, when is it linearly independent? So I say that this subset is linearly independent if any linear combination that is equal to 0 is trivial, so has 0 coefficients. So what does it mean in quantifiers? It means that if we pick any number of elements of A, let's say A1 through AN, and if we pick any coefficients C1 through Cn of R, if the combination of these AIs is equal to 0. Then for a linearly independent subset, we have that all these coefficients are equal to 0. Now let me give you some examples immediately. If R is any ring, then the set 1 in R is linearly independent. But if M is any R module, then the set containing any set containing 0 with 0 in A is not linearly independent. And this is because I present you a non-trivial linear combination that is equal to 0. So 0 is equal to 1 times 0. I pick C1 equal to 1 and A1 equal to 0. So A1 is an A. And C1 is not 0. Therefore, it is not a trivial linear combination. And A is not linearly independent. Linear independence can be reformulated as a unique expression for elements of submodule generated by A in terms of these elements in A. So proposition. So again we have the same assumption, ring R, R module M, and a subset A of the R module. Then A is linearly independent if and only if any element of the module can be written uniquely as a linear combination of A. Let me prove this proposition. The backwards direction is the easier of the two, because for this element M, pick 0, then 0 can be should be uniquely represented as a linear combination of elements of A. So which means that any linear combination should have 0 coefficients. And now let me go in the forward direction. So assume that A is linearly independent and take some M that is written as the sum C1 A1 plus etc. CMAN, and that is also equal to R1 B1 plus etc. RL BL with the CI's and RJ's in being coefficients in R and AI's and BJ's elements from A. So we can relabel BIs in such a way that, like, we can possibly extend the sequence of AIs by BJs. So, and possibly by taking zero coefficients, we can assume that M is written as a linear combination C1, A1 plus etc. plus C and AN. So N can also be increased by big N. And this side is R1, A1 plus etc. plus Rn, An. Now let us subtract the top line from the bottom. Let us subtract from the top line the bottom line. So it is equal to M minus M. C1 minus R1 A1 plus etc. Cn minus Rn An. And at the same time it is equal to 0 because it is M minus M. So by assumption on linear independence, all coefficients are equal to 0. Ci minus Ri is equal to 0. And this is the same as saying that for every I, Ci is equal to Ri. And so we got that this representation as a sum of elements of A is unique by possibly adding 0 summands. And I say that in module M over R is free if it has a linearly independent set of generators. Let's say that this set is A. In this case, A is called a basis of M. And the number of elements of A is called the rank of the free module M, and it is denoted by Rk of M, the number of elements in A. So rank works like dimension, and we will prove that rank is well defined, so any basis of a free module has the same number of elements. Before I go into this, I would like to give some examples. R is free as an R module. with the basis A consisting of just one element 1. R to the n is free with the basis consisting of the standard vectors. Standard quotient vectors 1, 0, 0, 0, 0, 1, 0, etc. through 0, 0, 0, 1. And if f is a monic polynomial, then the R module R adjoint x modulo f is free on the generators, on the set of generators 1, x squared, etc. through x to the power degree of f minus 1. And a non-example is, let's take Z mod 6Z. It is not free as a Z module. And this is because for any element in this module, 6 times this element is equal to 0, and we get a non-trivial linear combination that is equal to 0. So any set consisting of one element A is not linearly independent already. However, Z mod 6Z is free as a Z module, as a Z mod 6Z module. And we can take 1 as the generator of Z mod 6Z over Z mod 6Z. And this will be a basis. I just want to put a word on these kinds of elements. So I say that an element little m in M capital is torsion. If there exists a non-zero scalar R such that Rm is equal to 0. And the set of all torsion elements is denoted by tors of M. And it is a subset, but not necessarily a submodule. And M is called torsion free if the only torsion element is 0. If tors M only consists of the 0 element. And you can see that, for example, any element and z mod 6 in z mod 6z over z is a torsion element. So for example, as z modules, tors of z mod and z, all elements here are torsion.